Part 1. The science behind wet H2S damage. Pressure-containing refinery process equipment that appears perfectly healthy from the outside develops internal hydrogen damage that remains invisible until leaks, cracks, or catastrophic failures occur. The common thread behind many of these failures is not metal loss, not corrosion rate, and not mechanical overload. It is hydrogen. In wet H2S environments, atomic hydrogen, a product of corrosion enters steel, recombines deep within the metal, often causing pressure boundary component failure long before conventional inspection techniques reveal the threat. This hydrogen permeation into steel can present either as hydrogen blistering, hydrogen-induced cracking, HIC, stress-oriented hydrogen-induced cracking, SOHIC, or as sulfide stress cracking, SSC. To understand each of these damage mechanisms, we must first understand the journey of hydrogen itself. This is not a study of 4 separate damage mechanisms. This is the complete story of one mechanism taking 4 different forms. This technical briefing has been organized into 3 parts. Part 1 explores the science behind wet H2S damage, including hydrogen charging, environmental controls, and the operating conditions that govern susceptibility. Part 2 examines hydrogen blistering, hydrogen-induced cracking, stress-oriented hydrogen-induced cracking, and sulfide stress cracking in detail. Part 3 focuses on hardness, steel cleanliness, welding effects, inspection strategy, mitigation methods, examination preparation, and interview mastery. We begin with Part 1. The science behind wet H2S damage. Why wet H2S damage is so important. Among all refinery damage mechanisms, wet H2S damage is one of the most feared because it is often hidden, can develop internally without obvious warning, and can lead to sudden failures even in equipment that appears mechanically sound. Unlike ordinary corrosion, where metal is gradually consumed, wet H2S damage is fundamentally a hydrogen damage mechanism. The true enemy is not H2S itself. It is hydrogen generated during corrosion that enters and accumulates inside steel. Many engineers mistakenly study hydrogen blistering, HIC, SOHIC, and SSC as 4 independent mechanisms. In reality, they represent different outcomes of the same hydrogen charging process. Understanding how hydrogen enters steel, where it becomes trapped, and how stress influences its behavior is the key to mastering the entire subject. The hydrogen story, where everything begins. When carbon steel or low-alloy steel is exposed to water containing H2S, corrosion occurs. The corrosion reaction creates dissolved iron, atomic hydrogen, and iron sulfide scales. Normally, atomic hydrogen will recombine at the steel surface to form hydrogen gas and escapes harmlessly. Now, available sulfur in the system, a product of the degrading H2S, changes everything. Sulfur acts as a hydrogen recombination poison, preventing the normal combination of hydrogen atom to hydrogen gas. This is one of the most important concepts in wet H2S damage. Instead of allowing atomic hydrogen to combine and leave the surface, sulfur adsorbed to the metal surface, blocking hydrogen atom from active catalytic sites that would normally promote hydrogen gas formation. As a result, more hydrogen atoms are forced to enter the steel. Less hydrogen gas escapes, and hydrogen begins diffusing through the metal. This absorption process is known as hydrogen charging. The severity of hydrogen charging controls the likelihood of wet H2S damage. Why water is mandatory. One of the most commonly tested API 571 concepts is this. Wet H2S damage requires liquid water. Dry H2S alone does not produce hydrogen blistering, HIC, SOHIC, or SSC. Water may exist as sour water, condensed water, water-rich amine, separator water, reactor effluent water, accumulator water, or water droplets suspended in gas streams. Even a small amount of water can establish the electrochemical conditions necessary to generate atomic hydrogen. What happens after hydrogen enters steel? Once inside the steel, hydrogen moves through the crystal lattice until it encounters trapping sites. These include manganese sulfide inclusions, laminations, segregation bands, microvoids, dislocations, grain boundaries, weld imperfections, and other metallurgical discontinuities. Hydrogen accumulates at these locations. The final damage mechanism depends on steel cleanliness, hardness, strength level, residual stress, applied stress, welding history, microstructure, and environmental severity. The same hydrogen can eventually produce blistering, HIC, SOHIC, SSC, or a combination of them. The role of H2S concentration and H2S partial pressure. A major misconception is that only very high H2S concentrations cause damage. This is incorrect. Wet H2S damage can occur at surprisingly low H2S levels when liquid water is present. The critical parameter is not total pressure. The critical parameter is H2S partial pressure. As H2S partial pressure increases, hydrogen charging increases. Hydrogen absorption increases, and wet H2S damage becomes more likely. Greater H2S partial pressure generally means greater risk for blistering, HIC, SOHIC, and SSC. There is no universal safe H2S level applicable to all operating conditions. The role of pH. pH strongly influences corrosion activity and hydrogen generation. Risk generally increases when the environment pH promotes active corrosion. Particular concern exists in environments below a pH of 4. Corrosion activity becomes increasingly aggressive. Hydrogen generation increases. Hydrogen charging increases. Concern may also exist above a pH of 7 in certain sour systems, especially when contaminated by cyanides, ammonium bisulfide species, or other process contaminants. The engineer must always remember this. It is not pH itself that causes damage. pH modifies hydrogen generation and hydrogen absorption. The role of temperature. Temperature affects the various forms of wet H2S damage differently. Hydrogen blistering. Blistering can occur over a broad temperature range. It may occur from ambient temperatures to temperatures well above 150 degrees Celsius, provided that water remains present. H2S remains present, and hydrogen generation continues. The dominant factor is hydrogen uptake rather than temperature itself. Hydrogen-induced cracking occurs over a broad temperature range. It has been observed at ambient conditions and at temperatures above 150 degrees Celsius. The essential requirements remain hydrogen charging, susceptible steel, and internal trapping sites. Stress-oriented hydrogen-induced cracking. Generally following the same temperature behavior as HIC, SOHIC begins as HIC. The dominant variables are residual stress, tensile stress, hydrogen charging, and steel cleanliness, rather than temperature alone. Sulfide stress cracking, or SSC. SSC behaves differently. SSC susceptibility is generally highest near ambient temperature and at moderately elevated temperatures. The primary concern is typically below 93 degrees Celsius. As temperature increases above this range, SSC susceptibility generally decreases. However, blistering may still occur. HIC may still occur, and SOHIC may still occur. This distinction is a classic API examination question. The role of velocity. Velocity is not a primary control variable for wet H2S damage. However, high velocity can remove protective iron sulfide films, increase corrosion rates, increase hydrogen production, and increase hydrogen charging. The effect is indirect. Velocity influences damage by increasing corrosion severity rather than by directly creating cracks. Everything discussed so far answers a single question. How does hydrogen enter steel? In the next part, we move beyond hydrogen entry and begin examining what hydrogen actually does once it becomes trapped inside the metal. We will explore hydrogen blistering, hydrogen-induced cracking, stress-oriented hydrogen-induced cracking, and sulfide stress cracking, not as isolated mechanisms, but as connected outcomes of the same hydrogen charging process. End of part 1.